So the second regions we want to consider is a low temperature region, but when the magnetic field is 0. Then for the mean field approximation, this is the exact result in which y equals g times mu sub b times the spin quantum number s plus b plus, b mean field plus b divided by 3 kBt. Okay? Now we are dealing with low temperature but field equals 0, so you drop that. Note that the B or mean field is, where's the definition? All right. The number of nearest neighbors times the exchange integral j divided by g times mu sub b squared times n Avogadro times the magnetization, right? I have dropped these arrows. So the m shows up here. In other words, this contains the magnetization m as well as magnetization is here. So you can solve this equation numerically. You can do a numerical calculation and find the solutions. But historically, before the advent of computers, people did graphical way of qualitative finding what happens. So let's do that. And what you do here is you plot on the y-axis m over m sub s, and on x-axis you take y. Okay. Then Brillouin's function is nothing but cosine hyperbolic cotangent. So you can show that this qualitatively behaves that way, and it's linear for small y. And this is the part I gave you as a quiz, right? When y equals much, much smaller, y, 1 is somewhere around here, much, much smaller than 1, it's linear and has the functional form I told you. So this is the Brillouin's function. Okay, in which y has B or mean field. On the other hand, this equation, in which m is that, is a bunch of straight lines. So it could be a line like this when temperature is large. On the other hand, when the temperature is small, then the slope becomes small. Right? And this equation has a solution when those two lines meet each other. So when the temperature is high, this is a solution. In other words, y equals 0, which means the mean field is 0, and the magnetization is also 0. When the temperature is low, then you have two solutions, m equals 0, as well as m is non-zero. Y equals 0, as well as y equals non-zero. Okay, it has two solutions. And it turns out when the temperature is low, this solution is artifact of the mean field approximation. This is the true physically meaningful solution. Now you can see there is a critical temperature. When the temperature is such that the slope is g mu bs times this thing, divided by 3 kBt. If the temperature is just right, then the slope of this line will be exactly the same as this slope here. Okay? So when the temperature has this special value, and if you look at this, when the temperature is theta, it turns out if you consider the special temperature at which the slope of this straight line is the same as the slope of this Brillouin's function near y equals 0, then it turns out that that temperature is T equals theta. So low temperature, we mean temperature is less than theta, and high temperature, we mean temperature higher than theta. You can do only so much with the graphical method. Then the rest you have to do numerically. And if you did so, since theta is a special temperature, it's useful to divide the temperature with theta. And when the temperature is theta, in other words, T over theta is 1, M over M sub S is these two lines only cross each other at the origin, but as you lower the temperature, the crossing point goes to the right. With that, the magnetization increases. You get this kind of curve here, if you did the numerical calculation. This is when the spin is 1/2. As you increase the spin, the curve changes something like this, and this is when S equals infinite. And in between, as you increase the quantum number S, the curve changes like this. Okay? This is a numerical result, which is given in the handout. So this is the behavior of the magnetization, but this is when J goes positive. In other words, theta is positive. So in zero magnetic field, as you cool the ferromagnetic material, in zero magnetic field, magnetization is 0. And then at special temperature, namely Weiss temperature, the magnetization starts to show up, although the field is 0. That's why this magnetization is called a spontaneous magnetization. And this is the, in that sense, is the ordering temperature, below which the system somehow is an order. Therefore, the magnetic dipole moments are not pointing in the random direction anymore, but they spend more and more time in the same direction. Okay? They're somehow, they suddenly find a special direction. They suddenly decide and choose a special direction. And theoretically, as well as in materials, magnetic materials, for which the exchange Hamiltonian is a good approximation, as you cool a ferromagnetic material, suddenly the system decides, okay, this is the preferred direction, and the magnetic moments all line up in the same direction. If you cool the sample in a different shape or in a different environment, they all suddenly decide that this is a special direction.